Hello. In this video we will look at few factor calculation, define the according rules and use them. And the learning goals will center around these rules. The first one being the summation rule. So the sum of few factors over one object is 1. I'll get to that quite next. Then the reciprocal rule, which takes, let me just take the laser pointer here, which takes the other object into account, not just looks at where does radiation go to, but where does it come from also. Then we will make use of symmetry planes and auxiliary planes, and that will be towards the end of this video. But I will also bring an example how to do the calculation. Now the summation rule, so we sum over all the hit surfaces, that's the index J and index I, and the surface I sends out. So the radiation from that surface gets to all other surfaces around. Nothing gets lost, so the sum of the ratio of this radiation distribution is then 1. That's the sum of the few factors. Quick example, surface 1 sends out, radiation hit object 2, 3 and 4. So the equation is 512 plus 513 plus 514 equals 1. And the index, the first index is the sender, the second index is the receiver here. Now when we look at surfaces which are not flat, here a concave surface, then 1 not only sends radiation to 2, but 1 also can hit itself. In this case we have 512, this one, plus 511, the self-hitting few factor equals 1. And this one is often forgotten. So to make sure that you don't forget it, what you could do is, let me show it to you. You could just put that one into this equation and add plus 511. And if this later on, because the surface is flat, becomes 0, then at least you have not forgotten it. But we will train this and you shall see how this works. Now the reciprocal rule, and it says the area times the few factor equals the opposite area size times the opposite few factor. And that's A1, A2, and as stated above, A1, 512 is A2, 521. And then we can build these ratios, of course. For concave surfaces, that's nice, it works as well, because we just look at what hits 2 and what comes from 2 to 1. So A1 times 512 is A2, 521 as for the flat surfaces. But here we know that all radiation that's being emitted from 2 hits 1. There's no other chance for this surface here. So 521 is 1. And then I can calculate 512 as the area ratio. And that's a good example that if we use the reciprocal rule and we can make sure that one of the few factors is 1, then we can determine the other quite easily. Let's move forward with the symmetry. So here we can make symmetry by saying, well, 2 and 3 are the same size. So 512 must be 513. 4 and 1 are also the same, so 542 is 543, and that's written here. And the same for these few factors. So make use of symmetry whenever you see it. It makes your life here much easier. The auxiliary planes, here an example. These two objects are not right next to each other. So for radiation from 1, let me just draw a little bit, there may be a chance that it goes out here. So it would be good then to identify an auxiliary plane, and this auxiliary plane makes sure that all radiation from 1 that's not hitting 1 goes to that auxiliary plane. And for this we have here example 1, and what we ask is how much of radiation from area 1 reaches area 2 and vice versa. excuse me, and that's indicated by these brown arrows. And 3 is just there to complete the scenario, and we shall see that also in the next example. And if we calculate areas, also take into account here, let me just that typically we would consider kind of a unit depth or L, whatever. So if you calculate then an area, this parameter would fall out. So we can just live with what you see in the plane. So phi q dot from 1 to 2, that's a general formula. We don't know phi 1, 2 yet, but we can write down the formula. So that's phi 1, 2 times q dot 1, 2 primes times area 1. And the same we can define for the heat flux from 2 to 1. And now we solve, and we can make the summation rule for area 1. So as you notice, I've put in here a phi 1, 1, then plus phi 1, 2, plus phi 1, 3, and the colors indicate the surfaces. And we know that phi 1, 1 is 0, so the equation reduces to phi 1, 2 plus phi 1, 3 equals 1. The symmetry rule for area 1 is phi 1 to surface 2, which is the same size and same orientation than 3, is equal to phi 1, 3. So phi 1, 2 is 1/2, because all of the radiation that's sent from 1 into this direction here goes either to 2 or to 3. The reciprocal rule also holds, and with that we can calculate phi to 1, because we just calculated phi 1, 2, can put that in, and then we calculate the areas. A1 we just call by the diameter, and this is half of a semicircle, so this is pi times d divided by 4, quarter of a circle. And so the phi 2 to 1 is 2 over pi. Now a little bit more complicated. Now we have a real surface 3, and we are asked to determine the view factors, or to calculate how much radiation reaches the areas 1, 2, and 3 from area 2. So again, we can write down these 3 formulas: q dot 2 to 1, q dot 2 to 2, q dot 2 to 3. And just generally write down the equations using view factors times surface brightness. As I mentioned in the last video, this expression we call surface brightness. For the moment, just accept the name. I will define what that is further on in the other videos. And now let's look at how we can solve the thing. First again, summation rule for the area under consideration, area 2. Phi to 1 plus phi to 2 plus phi to 3 is 1. And phi to 2 is non-zero, so we have really 3 view factors here. And to calculate phi to 2, we are using an auxiliary plane. And that auxiliary plane goes here, and it's drawn in a way that all the radiation from 2 hits that auxiliary plane. No, that's wrong. All radiation from the auxiliary plane hits 2, because some of the radiation from 2 hits itself, and that makes this view factor calculation a little bit difficult. Now, summation rule for this area h, phi h to 2 plus phi h is 1, and phi h, that's a straight line, is 0. So phi h2 is 1. All the radiation from this auxiliary plane h reaches surface 2. The reciprocal rule can be put up as well. So phi 2h times a2 plus phi h2 times ah And phi h2 is 1, so we can calculate phi 2 to h as the area ratio here. And if we put the areas in, then we have this secant, and we have the bow. So that's d over square root 2 divided by pi d over 4. So this is the square root of 8 divided by pi. That's a view factor from 2 to h. Now we have to do the summation rule for 2 with the auxiliary plane. Phi 2 to h plus phi 2 2 is 1. And now this one I just determined, I can calculate phi 2 2, the self-hitting view factor. So this is 1 minus phi 2 h, and this is 1 minus square root 8 over pi. So by using the auxiliary plane, I could calculate phi 2 2. And from the first summation rule, I can now determine phi 2 3. Phi 2 2 I know, phi 2 1 I got examined on the last slide. So phi 2 3 is this expression, and at the end it's 2 times square root 2 minus 1 divided by pi. To help you do some geometrical considerations, we have in the app quite some problems defined that use view factors for different radiating surfaces and also auxiliary planes, which are indicated like here. Let me use the laser pointer again. So auxiliary plane, enclosed object, specific surfaces, and so on. So go to the app, train, and you'll get a good feeling for these view factors. With that, I come to the final questions that you should be able to answer. First one, which rules are used for view factor determination? And the second one is, for which body shapes do we have to consider this phi II, so the self-seeing view factor? Thanks for listening.